So yeah, I'm going to tell you about how we can use the idea of topology abstraction in networks to improve synthesis of network configurations. And this is joint work with Todd Millstein, Ratul Mahajan, Padhye, and my advisor, David Walker. So computer networks are playing a more and more central role in our everyday lives as more people gain access to devices around the world and more companies move their critical services into the cloud. But there's a big problem, which is that computer networks are extremely error-prone and they're hard to configure correctly. And this manifests in the form of large-scale network outages that happen every couple of months or so. And these outages can affect the lives of many, many people, and there are entire websites devoted to basically tracking these types of outages. So one of the reasons why network outages are so common is because most networks that exist today run what are called traditional networks. So these run distributed routing protocols that have been around for decades. And to configure these protocols correctly, you have to actually write a configuration for every single device in your network. And you have to specify what kinds of routes these devices communicate with their neighbors and how they choose a route and so on. And so the problem is that configuration is very hard because you're essentially writing a distributed program. And so it's hard for a number of reasons. So one is just the sheer complexity of the task. So to configure a network, I typically have to write a configuration for every device in my network. These configurations can be tens of thousands of lines long. And I have to do this for upwards of thousands of devices in modern networks, which are growing increasingly large. If I look at a particular configuration file, which is provided by these hardware vendors, the languages that they provide are extremely low level. They typically look like assembly code, and they have a bunch of low-level protocol parameters that you have to figure out how to configure. And basically, the task you have to do then is write these low-level configurations for every device such that the emergent behavior of the network does what you want. And this is made even more complicated by the fact that networks are dynamic, and so things fail all the time in large networks. Links and routers go down, and so now figure out how to make this correct when things can fail arbitrarily. And of course, humans just can't reason about all possible combinations of failures, so this is just a very hard task. So people have tried to address this problem in the past with synthesis tools. In particular, there was a paper in SIGCOMM 2016 that we authored before, which had the idea that you take a network-wide routing policy where you don't have to think about the fact that this is a distributed system. You take some collection of fault tolerance requirements and a concrete network topology, and then from that you synthesize these low-level device configurations for a routing protocol called BGP. However, to our surprise, when we actually tried to sell this idea to network operators, they were very reluctant to use this type of technology for a number of reasons. So the first is that networks are huge. So you need a tool that can basically scale to these massive networks with thousands of devices, and you need to be able to do synthesis on human timescales that people can quickly iterate on. The second is that it's very hard to debug these kinds of configurations. If you're generating thousands of configurations on devices, these hardware devices are known to have bugs, and so it's very hard to figure out what's going wrong if these things are automatically generated. And then finally, if you want to change your network in any way by incrementally expanding your network or adding some feature, it's very difficult with these synthesis tools to do this because you can rerun the tool on the same input with a slightly modified network, and you're going to generate potentially completely different configurations. And so if you tried to actually deploy this in practice, what that would mean is you have to go log into every device in your network, shut it down, reinstall the configuration, and then bring it back up. And of course, if you do this for every device, you have to effectively shut down your entire network. So ideally, what operators would like is the following. So you want some way to write high-level programs about what your network should do. So you shouldn't have to think about the fact that it's distributed. You want a tool that can basically generate these configurations in a scalable manner. It should be easy to debug, and it should be easy to incrementally modify and deploy without having to make sweeping changes to everything. So in our previous work called Propane, we tried to tackle this first problem about network-wide abstractions. And so today I'm going to talk about how we can extend these ideas using abstract topologies to get all three of these nice other properties as well. Okay, so if people aren't using these types of tools in practice today, then how do they deal with this complexity at the moment? And so the idea is that right now, if they have some large network, like the one I'm showing on the slide here, where you have a collection of devices, so this would be a data center, what they typically do is they collect these devices into what are called roles. So these are devices that play a similar function in the network, but might vary in small details. And rather than authoring one configuration file for every device in the network, instead what they do is they author a single template file for every role in the network. And so these templates typically are the same type of low-level configuration as before, but they add things like control flow with for loops and if statements, which iterate over some values from a database, and they populate the individual routers with particular values from this database. So there might be some variables that, again, get instantiated specifically on each device, but the vast majority of the configuration is shared. And so on the one hand, this is really nice because it tells you exactly what's different and what's the same in these configurations. But on the other hand, it doesn't really solve any of these problems. You're still writing a distributed system. It's just now a parameterized distributed system. It's very hard to think about whether or not this is correct. And again, making any small change is really dangerous nowadays. There's a lot of thought that goes into this because templates that work in one network might not work again when you make a small change to the network. Okay, so the high-level idea with abstract topologies is that rather than synthesizing these configurations from a concrete topology and a concrete policy, instead what we're going to do is we're going to create an abstract network topology and an abstract policy over that abstract network topology. And rather than generating configurations, we're going to generate these templates. And what we are going to show is basically that if we get any concrete topology that matches this abstract topology we wrote, and we instantiate the templates with that concrete topology, then we get the same low-level configurations that are going to work for this new concrete network. And this is nice for a couple of reasons. So first of all, because we're doing the hard, expensive part of synthesis over this abstract network, it's significantly more scalable. So instead of dealing with a network with thousands of devices, we're going to deal with a more abstract network that maybe has 5 or 10 devices in it. In addition, it's much easier to debug the output because you're generating these parameterized templates that humans can inspect. And then finally, we can incrementally deploy the network because if I make some small change to my topology that still matches this abstraction I wrote, then I know that the same templates I generated before are still going to work in the new network. And so I don't have to make changes to any of those devices. Okay, so to get an example of what this looks like in practice, I thought I'd show how people go about configuring a typical kind of data center network. And so I'm going to talk about various types of requirements people have on the left-hand side. And on the right, I'll point out how these get implemented today, and I'll try to avoid going into too many details since it involves understanding of these protocols. So the first thing people want is typically some sort of complete internal connectivity of their network. This is done in these protocols by injecting routes at various points in the network. In this particular data center, I've divided it up into global services and local services in different parts of the network, the left and the right. And so you might have constraints like I want traffic to be reachable for global services everywhere in the network, including outside my network. Local services in my network should be reachable only inside the network. And this can be done using various types of low-level filters. I might want it to be the case that traffic paths are what's called valley-free. So you never have traffic go down and then back up in a data center, which would be a very inefficient form of routing. I might want to make sure that traffic for external destinations leaves through my neighbor N1 if possible, because that's a more highly optimized network rather than my neighbor N2. And I might have a constraint that, for example, I don't want to allow traffic to go through my data center between my two neighbors, because again, this would be very inefficient. Right, so you can see basically to implement this today, you have to essentially scatter policy all over the network. And it's really hard to think about whether this is doing the right thing. And if I have something like I want to ensure that this policy I've implemented is robust for any combination of two failures, again, this is really hard to reason about. And in fact, this gets even worse if I now want to expand my network. So for example, if I want to add 2 new routers to the spine of my data center, and I reconfigure the wiring accordingly, the connectivity, when you consider both the topology and the routing policy, can actually change in this expanded version. So for example, maybe before I was robust to 2 failures, and now I'm only robust to a single failure. Okay, so let me go through the same example, but I'll show how we can configure this using Propane AT, the synthesis tool. I'll talk about how we can first describe an abstract topology, and then how we can write our routing policy over this topology. Okay, so the idea with this topology abstraction is that we want to create a much simpler topology like the one I'm showing on the right, which sort of at a high level captures all of the concrete instances of the network that we have now or might consider in the future expanding the network into. So here, basically, I've described a mapping from concrete networks, so the data center and the expanded version I had before, So I have a mapping from concrete nodes into these abstract nodes, which are called roles on the right-hand side. And the color shows how the nodes map in the concrete networks to the abstract one. And I've basically divided the abstract network into 5 roles. So there's a spine role and top of rack global service role, local service role, and so on. So we've divided the network so we can distinguish between the local and global services. Of course, this permits too many networks, so we might want to refine this abstraction by describing the kinds of connectivity invariants that exist between abstract roles in the network. So for example, I can have this variable called E3, which represents the number of edges leaving any device in the yellow role to going towards any devices in the pink role. And I can add a constraint, for example, that says the number of such edges in any concrete network I care about is greater than or equal to 2. Similarly, I can add a constraint that says that the number of edges going down from any pink device to any yellow devices is greater than or equal to 2. And these are shown in red on the left. Of course, in many networks, they're actually much more structured than this. So we can create a stronger invariant by capturing this repeated structure. So if you notice, the green and yellow devices are captured in this repeated structure of groups of 4 called pods in networking literature. And so I can draw a box around these devices to indicate that I want to talk about constraints in terms of these pods instead of all of the devices. So for example, now I can add a constraint that says the number of edges going down from any pink device to any collection of yellow devices per pod is at least 1. You can also add constraints that relate variables. So for example, I can say that the number of edges leaving each green device in the concrete network going towards yellow devices in each pod is equal to the number of yellow devices. So this would, for example, capture the fact that these are in a complete full mesh. And then you can add other constraints that use operations like mod, addition, subtraction, multiplication, and so on. Okay, so the next thing we need is a way to describe the routing policy of the network. And so our language for describing routing policy needs a couple of things. So we need a way to talk about what kinds of traffic we're interested in, which we use predicates for. We need a way to describe locations in the network and a way to talk about constraints that indicate which paths you want to allow, disallow, or prefer in the network. Okay, so here's an example of one of these propane AT routing policies over this abstract network. So the first thing I'm going to do is define a collection of constraints. And on the left-hand side, I have some predicate describing traffic. And on the right-hand side, I have a constraint. So the first line is saying that for any global prefix described by this purple template variable, which you can think of as basically grabbing any number of global prefixes destinations from some database, I'm going to add the constraint that routing for that traffic should end up, the final destination should end up at the TG role, which is where the global services are hosted. Similarly, for local prefixes, I might have the constraint that they should end up at the TL role. And for any other kind of traffic which is captured by the true predicate, I want to leave the network through N1 or N2. And I'm going to have a preference for N1 over N2, which is indicated by the 2 arrows here. I can also add additional constraints. So for example, for local prefixes, they should always use a path that at each hop along the path matches an internal router. So this would prevent, for example, leaking traffic to outside of the data center. I can say for all traffic, I want to prevent using valley paths by using this no valley constraint. And finally, I can prevent using paths that go in my network between my 2 neighbors by saying that for all traffic, I want to not allow paths that both enter from a peer and exit from a peer, where a peer is N1 or N2. And so that's all you write. You basically just tell the tool that you want to satisfy all of these constraints. You write this single file for the entire network, and you don't have to refer to the fact that this is a distributed system. And it should go off and find these templates that are basically incrementally deployable and expandable and do the right thing. Okay, so let me talk a little bit about how we actually do this configuration synthesis now. Basically, we break this up into the 3 steps. The first is to create an abstract intermediate representation that combines the policy and topology together. We then do a static analysis for the fault tolerance checking, which operates on the abstract network and infers invariance about connectivity for all underlying concrete networks. And then we can use this intermediate representation to generate BGP, basically this protocol called BGP, templates for that protocol, again, that are going to work for any concrete instantiation of the network. So the first step about translating to this intermediate representation, the idea is to basically first, we do a simple syntactic substitution where we combine all of the constraints on a per traffic class basis. For each traffic class, we then generate a sequence of automata where each automaton represents the types of paths that are allowed by the constraints the user wrote. So for example, when we said we preferred that external traffic leaves through N1 over N2, this would create two automata. The first automaton would basically capture paths that leave through N1 and then accept. And the second one would capture paths that leave through N2 and accept those paths. We can then intersect these automata with the actual network, abstract network topology to create an intermediate representation where it captures both the topology and the policy together. So the idea is that we generate a new graph such that every path through this graph is both a topology path and a path that's allowed by the constraints that we wrote. Right, so the task then is basically to figure out or to infer various types of connectivity invariants over this abstract representation so we can use this in our synthesis. And in particular, the question we want to answer is, how many disjoint paths are there between any concrete devices in two abstract roles in any worst case network? And so at a very high level, what's happening is basically we're going to iteratively compute the number of disjoint paths from sources to destinations. The idea is that we have a collection of inference rules like the one I've shown on the left here, where it tells you basically, given a fact you know, how can I infer a new connectivity invariance given what I know? And so the idea then is basically we can use a max SMT solver because we're interested in finding the worst case concrete network with respect to connectivity. We can ask the max SMT solver to basically minimize the connectivity given the constraints that the user wrote in their topology. I think it's a really cool algorithm, and I don't quite have enough time to go into it, but you can read our paper if you're interested in seeing more details. The next step is to do this template generation process. This is based on this previous work in propane, but modified slightly for this abstract setting. It involves some understanding of network protocol details that, again, I'm not going to have time to go into. But at a very high level, the idea is that we're doing a sort of domain-specific search for particular low-level local parameters of these devices. And because we're generating a configuration for each abstract device in the network rather than each concrete device, you can think of these as basically creating templates rather than configurations. The theorem we prove about this synthesis process is that if you start from an abstract network and an abstract routing policy, and you first concretize that into a concrete network and a concrete policy by filling in these template variables, and then perform the synthesis from there to generate these low-level configurations. This is equivalent to first synthesizing these templates from the abstract network and then concretizing those to the low-level device configuration. So either way you go, it's the same. And the cool thing about this is that if you take this top path, again, you're doing the expensive part, which is the synthesis, over this abstract network, which is significantly smaller. And additionally, because we did this fault tolerance analysis for the worst case concrete network, and because the abstract network doesn't change as long as we change the concrete network in a way that still matches that abstract network, we can expand our network or take routers away, and we can know that we can basically reuse the same templates since none of the inputs to the tool have changed. And so this lets us basically incrementally deploy our network without having to worry about network-wide changes. So we implemented this in F#. We currently generate Quagga and Cisco, which are two popular vendor configuration languages. We use NewZ, which is a max SMT solver, to do this fault tolerance analysis. And we basically, to evaluate this tool, we looked at two things. So first of all, can we express networks that are actually used in the real world today? And can we do this analysis precisely? And then finally, how fast does the tool actually scale on these real networks? So we looked at a collection of topologies for data centers and transit networks that are commonly described in network literature. And we looked at two variants of routing, so something called valley-free routing and something called shortest paths routing on both of these. And we tried to see, so for the expressiveness, basically we were able to encode all of these topologies without fixing any particular parameter, which these topologies are usually described in terms of. For some of the later topologies, like recursive topologies like dcell and bcube, we have to fix some particular parameter, but not others that's used in the topology. We also checked if we could accurately find reachability between some or all pairs of devices using this fault tolerance analysis, and found that basically for all of these networks, we could precisely infer whether or not all pairs of devices were reachable or not. And for just inferring whether or not there are k-disjoint paths precisely for all of these topologies, we were able to infer many of them precisely, but we're conservative, which is indicated by the C, for some of the more difficult topologies like the recursive ones, B cell and D cube. In terms of compilation synthesis time, basically we looked at taking configurations from a large cloud provider and converting them into our synthesis language. And we looked at compiling these into templates versus configurations for increasingly sized networks for both data centers and transit networks, which are by far the majority of real-world networks that are used today. For the concrete network, we found that basically the synthesis time would grow, as you'd expect, quite dramatically as you get to larger and larger networks. And so when you get to many thousands of devices, the configuration would take on the order of hours to days for the concrete setting. And for the abstract setting, what we found is that we were able to do the synthesis in under 10 seconds in all cases, again, because the size of the abstract network doesn't really grow as the concrete network grows. So just to wrap up, this is a new network synthesis tool. It works by using this idea of topology abstraction in networks. We can generate concrete configurations from these templates, and we know that any concrete instance of a network is basically going to be correct given the templates that we generate. And then finally, using this abstraction, we can get high scalability by synthesizing over this much smaller abstract network. And the code is available as open source on GitHub, and I'd be happy to take any questions. Thank you.
That was really great. Thank you. I really liked how you were able to talk about something that I didn't really know about in a way that was very clear. So I had a quick question about the abstract topology part. So you said that one of the main benefits was the fact that whenever you do add, for example, a router, you'll be able to make incremental changes much easier. So what I'm confused about is I thought that if you were to add a router, then that'll change the abstract topology also. So then the old concrete topology won't match the new abstract topology. So then how are you able to get the incremental changes?
So the concrete topology is only used as an input when you're doing the concretization part. So when you add some new devices to the concrete network, when I say it still matches the abstract network, I mean is basically you still have some mapping from nodes to nodes. And all of the invariants that you wrote, like the number of outgoing edges and incoming edges, has to still be that still has to be true, valid, given the concrete network you wrote. And so if those conditions are true, then the same templates are going to work. And so when you concretize the network using this new concrete network, all of the devices that used to exist are still going to get concretized to the same exact configuration they had before. And the new devices might have new configurations, but that sort of is something you have to do no matter what.
All right, great.
Other questions?
So some properties like value freeze are very hard to hold in a failure scenario. So does your language has a way to say, in case of a failure, it can degrade a bit the service, but not too much? Because it's easy, for example, to solve value free. I mean, if you have one level of going up, but value free is very hard in case of failure, for example. So.
Yeah, that's right. In fact, there are certain times where you can have bugs if you implement value-free routing under certain failures where you might not have them if you did, for example, shortest paths routing. So right now, the sort of model is that the way we generate these configurations should hold under all possible failures. So when I wrote the constraint that I wanted value-free routing, what that means is that if the only route in the network is a non-valley, is a route with a valley in it, it simply won't be used. So that's like how we currently handle that. So there's no way to say, for example, that I want to use value-free routing only under certain circumstances, like before a certain number of failures occur. And sort of the more practical reason why this happens is because these distributed protocols actually have no way to know this. Like you actually can't implement it. because they know only, in some cases, yeah. So for example, in this BGP protocol we're targeting, the devices have no notion of which other links have failed in the network other than ones that they're directly connected to. And so this certainly could be interesting, I think, in the future, but it's not something we can do at the moment.
All right, we have time for a couple more questions.
Wonderful talk. The properties that you described in your language with the keywords like nil valley, are those primitives or keywords in your language, or can you define arbitrary predicates over the kinds of paths you'd like in your network?
Yeah, so you can define, so basically these are all just syntactic sugar for regular expressions. So you can define new constraints by defining functions and everything. And so most of these that I showed are actually just defined already by the language. They're not like primitives built into the language or anything. There are a few primitives, just, yeah, as you can imagine. But yeah, again, it's very easy to extend.
Cool. Can I ask another question? Sorry. How closely does the language you use for expressing restrictions on your graphs match up with the kinds of templates that show up in BGP? Was your design inspired mostly by what exists in BGP templates, or more from like the literature on graph generator languages or something like that?
Yeah, so this was definitely inspired by like what people have today. So the configuration templates we generate are actually fairly similar to like the types of configuration templates people write by hand today. There are some differences. So for example, sometimes the tool will generate, will decide to implement something in a very different way. So for example, it will use something called community tags in BGP to tag information at one location and then use that information later in the network. Whereas other people, like humans, will often write these things called regular expressions, where you can match the path that something took. And they're essentially doing the same thing, but it's kind of a slight difference in terms of how it actually generates it.
Thank you.
Thanks.
Let's thank the speaker.